Welcome to the Deep Dive. Today, we're settling in to unpack a stack of sources, all centered around one magnificent planet, Saturn.
Yeah, we've got quite a range here. Material covering everything from, ancient observations right up to the really revolutionary insights from modern space missions like Cassini.
So our mission for this deep dive is to help you look past Saturn's iconic rings, obviously, and quickly get informed on the most important and maybe surprising nuggets of knowledge hiding in these sources.
Sounds good. Let's jump in and see what we can uncover about this truly incredible world.
Okay, let's start with the fundamentals then. We all know Saturn is the sixth planet from the Sun, and it's the second largest after Jupiter.
Right, and it's classified as a gas giant, composed primarily of hydrogen and helium, the usual suspects for these big guys.
But here's where it gets, well, really interesting right off the bat. These sources point out something pretty strange about its density.
Despite its immense size, its radius is about 9 times.
Yeah.
Saturn's average density is significantly less than water. Less than water? You're kidding.
Nope. We're talking 0.687 grams per cubic centimeter. Water's density is 1 gram per cubic centimeter.
So that old analogy, if you had a giant cosmic bathtub, Saturn would actually float.
It would. It's a great way to picture it, even if it's totally impossible, but it really highlights how low its density is.
That's wild. And it helps explain why, even though it's, 95 times more massive than Earth?
Yeah, over 95 times Earth's mass, but still less than a third the mass of Jupiter, even though they look, roughly similar in size.
So it's just puffier, less compressed than Jupiter.
In a way, yes. The sources also make it clear it lacks a definite surface like Earth, and because it spins incredibly fast.
Right, it's not perfectly round.
Exactly. It's noticeably flattened at the poles and bulges out at the equator. The equatorial radius is actually more than 10% larger than its polar radius.
10%, that's a lot. More flattened than the other gas giants, then.
Yeah, this oblateness, as they call it, is more pronounced on Saturn. And that spinning, bulging shape must affect things like gravity, right?
It absolutely does. Gravity isn't uniform. It's lower at the equator, around 8.96 meters per second squared.
Which is actually less than Earth's surface gravity.
That's right. But at the poles, it's stronger, about 10.44 meters per several. Of course, if you wanted to leave Saturn.
The escape velocity, much harder.
Much, much harder. The equatorial escape velocity is nearly 36 kilometers per second, way higher than Earth's.
Okay, so relatively easy to stand on, if you could stand, but very hard to jump off. That gives us a good picture of the outside. What about peering inside? What do these sources tell us about Saturn's interior?
Well, the models derived from the data suggest a structure somewhat like Jupiter's, but, more centrally condensed, more mass packed towards the middle.
So denser core.
Probably. There's likely a small rocky core, compositionally similar to Earth's core, maybe, but denser.
How big are we talking?
The estimates have changed a bit over time. Older figures suggested maybe 9 to 22 times the mass of Earth. But more recent data, using something called ring seismology.
Ring seismology. You mean studying the rings tells you about the core?
Kind of, yeah. It's fascinating. Internal vibrations within Saturn actually cause ripples, waves in its gravitational field.
And those waves affect the rings.
Exactly. They create patterns in the rings, especially the C ring. By analyzing those patterns, scientists can infer things about the deep interior, like the core.
That is incredibly clever, using the rings like a giant planetary seismograph.
It really is. And this newer data suggests maybe a larger but more diffuse core, around 17 Earth masses perhaps, with a diameter of about 25,000 kilometers. Still quite substantial.
Okay, so a core, possibly diffuse. What's around that?
Surrounding the core, there's thought to be this thick layer of liquid metallic hydrogen.
Hydrogen acting like a metal under that much pressure.
Exactly.
Yeah.
Compressed so intensely it becomes electrically conductive. Then above that, a layer of liquid molecular hydrogen, but it's saturated with helium.
Helium mixed in.
Right. And that gradually transitions to just gas in the outermost 1,000 kilometers or so, the interior.
And we know Saturn generates a lot of its own heat, don't we?
A huge amount. The core temperature might be around 11,700 degrees Celsius. The planet actually radiates about 2.5 times more energy into space than it receives from the sun.
Wow. Is that just leftover heat from formation, like Jupiter? That Kelvin-Helmholtz thing?
That gravitational compression, the Kelvin-Helmholtz mechanism, is definitely part of it. But the sources suggest it might not be the whole story for Saturn, especially compared to Jupiter. It doesn't seem quite sufficient.
So there's another idea.
Yes. An alternative, or maybe an additional process, involves helium essentially raining out deep inside the planet.
Helium, rain. How does that work?
Under the intense pressure deep down, helium is thought to separate from the hydrogen, forming droplets that are denser. These helium droplets then sink towards the core.
And that generates heat.
Yes, through friction as they fall, releasing gravitational potential energy as heat. It would also explain why the outer layers of Saturn's atmosphere seem somewhat depleted of helium compared to Jupiter.
Helium rain. That sounds completely science fiction.
It does, doesn't it? And speaking of wild things, some sources even speculate about, well, actual rainfalls of diamonds potentially occurring within Saturn's atmosphere.
Diamond rain. Okay, Saturn's interior is way more dramatic than I realized. Let's move outwards to the atmosphere we can actually see. What's that made of?
Okay, the outer atmosphere is, unsurprisingly, mostly molecular hydrogen, about 96.3%. And then helium makes up most of the rest, around 3.25%.
Just those two, mostly.
Primarily. The remaining fraction includes trace amounts of things like methane, ammonia, ethane, other hydrocarbons, and some heavy elements.
And that familiar pale yellow color we see in pictures.
That comes from ammonia crystals floating high up in the upper atmosphere. Those crystals give it that characteristic pale yellow hue.
Does it have weather patterns like Jupiter's bands?
It does have banded patterns, yes, similar to Jupiter's zones and belts, but on Saturn, they tend to be fainter, less distinct, and wider, especially near the equator.
And the winds. I remember reading the winds are incredibly fast.
Oh, they are truly extreme. The sources state they're the second fastest sustained winds in the solar system after Neptune's. They can reach speeds up to 1,800 kilometers per hour near the equator.
1,800 kilometers per hour. That's hard to even comprehend. Faster than the speed of sound on Earth, nearly.
It's phenomenal speed. And like Jupiter, the atmosphere has distinct cloud layers based on temperature and pressure.
So different chemicals condense out at different depths.
Exactly. You've got ammonia ice clouds in the upper layer, then below that, clouds of ammonium hydrosulfide ice, and deeper still where it's warmer, you find water ice clouds and even water droplets.
And there's chemistry happening too.
Yeah.
Driven by sunlight.
Yes, ultraviolet radiation from the sun triggers chemical reactions high up. Methane photolysis, for instance, breaks down methane, leading to the formation of more complex hydrocarbons like ethane and acetylene, which then get transported downwards by atmospheric circulation.
So incredibly fast winds, layered clouds, complex chemistry. But the atmosphere isn't always just hazy bands, right? It has some really big, strange features sometimes.
That's where Saturn gets really interesting, visually. While it often looks quite bland compared to Jupiter, it periodically features these enormous, long-lived storms and oval features.
Like its own version of the Great Red Spot.
Sort of, but maybe more episodic. The most famous example is the Great White Spot.
The Great White Spot. Sounds impressive.
It is. It's a huge storm system, an eruption of clouds from deeper levels that appears near the equator roughly every 30 Earth years.
Every 30 years, like clockwork.
Roughly, yeah. It coincides approximately with one Saturnian year and seems to occur around the time of the Northern Hemisphere's summer solstice.
Have we seen many of these?
The sources list observations going way back. 1876, 1903, 1933. That one was particularly well observed then, 1960, 1990. And the most recent major one in 2010.
And these things are huge, right?
Enormous. They can spread out to encircle a large part of the planet. And what's really fascinating is that even after the visible storm fades, instruments like Cassini could detect lingering thermal signatures, like disturbances deep in the atmosphere lasting for years afterward.
Wow. So these storms really leave a mark. What else is unusual up there?
Well, sometimes the northern hemisphere can take on a striking bright blue hue.
Blue, like Neptune or Uranus.
Similar idea. It's thought to be caused by Rayleigh scattering, the same process that makes Earth's sky blue becoming more prominent when the upper atmosphere is particularly clear of haze.
Okay, and then there's something strange at the South Pole, a warm spot.
Yes, a warm polar vortex at Saturn's south pole. It's actually the only known example of a warm polar vortex in the entire solar system.
Warm being relative, I assume.
Oh, absolutely. Average temperatures on Saturn are frigid, maybe minus 185 Celsius. But inside this vortex, temperatures can reach a comparatively balmy minus 122 degrees Celsius.
Making it the warmest place on the planet. Still incredibly cold, but warm for Saturn.
Exactly. But the visual feature that just blows everyone away, the one that looks like nothing else.
Has to be the North Polar hexagon.
That hexam, absolutely. First properly imaged by the Voyager probes, this isn't just a storm cloud. It's a persistent wave pattern in the clouds embedded in the jet stream encircling the North Pole.
And it's perfectly hexagonal.
Remarkably so, and it's enormous. Each of the 6 sides is about 14,500 kilometers long.
Wait, 14,500 kilometers per side.
Mhm.
How big is that compared to Earth?
Each side is longer than the entire diameter of Earth.
No way. That's absolutely immense.
It is, and what's perhaps even weirder is its stability. It rotates with a period that precisely matches the planet's radio emissions period, about 10 hours, 39 minutes, 24 seconds.
So it's somehow locked to the planet's deep rotation. It doesn't drift like other clouds.
That's the thinking. It doesn't seem to shift in longitude relative to the planet's interior spin, unlike typical atmospheric features.
Do we have any idea why it forms? Why a hexagon?
It's still a bit of a mystery. Laboratory experiments using rotating fluids have actually managed to replicate similar stable polygonal shapes under certain conditions, which provides some clues about fluid dynamics.
So it might be a natural consequence of rotating fluids on that scale.
Possibly. But why only at the North Pole? The South Pole also has a strong jet stream and a polar vortex, but no hexagon. So the exact conditions remain speculative.
Okay, so we've got wild weather, bizarre stable shapes. What about the invisible forces? Let's talk about Saturn's magnetosphere.
Right. Saturn does possess a significant magnetic field. And surprisingly, compared to, say, Jupiter's complex field, Saturn's is remarkably simple and symmetric. It's almost perfectly aligned with its rotation axis, like a classic dipole magnet.
Simple. Is it strong, though?
Well, its surface strength at the equator is actually quite a bit weaker than Earth's, and only about 1/20th of Jupiter's powerful field.
Weaker than Earth's.
Huh. But because Saturn itself is so huge, its overall magnetic influence, what they call the magnetic moment, is enormous. It's about 580 times greater than Earth's.
Ah, okay. So the field itself isn't super intense at the surface, but its reach is vast. And what generates it?
It's believed to be generated by electrical currents flowing within that layer of liquid metallic hydrogen deep inside. A metallic hydrogen dynamo process, similar in principle to how Earth's field is generated in its liquid iron core.
And this field creates a protective bubble, the magnetosphere.
Yes, it carves out a large cavity in the solar wind, deflecting most of those charged particles streaming from the sun.
Does anything else contribute to what's inside the magnetosphere?
Interestingly, yes. The moon Titan, with its thick atmosphere, actually loses some atmospheric gases that become ionized and contribute plasma-charged particles to Saturn's magnetosphere.
So Titan is feeding the magnetosphere.
In a way. And just like Earth, interactions between the magnetosphere and particles cause aurorae, northern and southern lights, near Saturn's poles.
Okay, this actually ties into something you mentioned earlier, the puzzle of Saturn's rotation period. The magnetic field plays a role there, right?
It does, because the magnetic field's rotation is what generates the radio emissions we use to try and measure the planet's internal spin. But it's been tricky.
How so?
Well, early measurements back in the Voyager era, based on those radio emissions, suggested a rotation period of about 10 hours, 39 minutes, 24 seconds. That was considered System 3 rotation.
Okay.
But then the Cassini spacecraft, years later, measured radio signals, suggesting a slightly longer period, around 10 hours, 45 minutes. It even seemed to vary slightly over time.
So the radio signals weren't stable. That's odd.
Very odd. And it led to a lot of head scratching. But then came that ring seismology technique we talked about, looking at the waves in the sea ring caused by the planet's internal oscillations.
Right, probing the inside via the rings.
And that analysis suggests a much more precise internal rotation period, closer to 10 hours, 33 minutes, 38 seconds, significantly shorter than the later radio measurements.
So why the discrepancy? Why would the radio signal give a different answer?
Well, one leading theory emerging from Cassini data points the finger at Enceladus.
The moon with the geysers. How could that affect the radio signal?
The idea is that the water vapor erupting from Enceladus's geysers gets ionized, charged up, and forms a plasma torus around Saturn. This plasma interacts with Saturn's magnetic field lines, and this interaction might actually be creating a drag on the magnetic field lines in the outer magnetosphere where the radio signals originate, effectively slowing down their apparent rotation rate relative to the planet's deep interior.
So the moon is literally messing with our measurement of the planet's day by gumming up the magnetic field.
That's the gist of the theory. It's a fascinating interplay between the planet, its moons, and its magnetosphere, making a seemingly simple measurement surprisingly complex. The puzzle continues.
That's incredible. A moon interfering with how we measure the planet's spin. Okay, speaking of timescales, what about Saturn's journey around the sun, its orbit and year?
Saturn orbits the Sun at quite a distance. On average, it's over 1.4 billion kilometers out, which is about 9 astronomical units, or 9 times Earth's distance from the Sun.
And that means a very long year, right?
Very long. One orbit, one Saturnian year, takes about 29.5 Earth years. Or, more precisely, about 10,759 Earth days.
Almost 30 Earth years for one lap around the Sun.
Exactly. And it moves along that orbit at an average speed of about 9.68 kilometers per second.
Does Saturn have a tilt, like Earth does, causing seasons?
It does. Its rotational axis is tilted by about 26.73 degrees relative to its orbital plane. Very similar to Earth's tilt, actually.
So it definitely has seasons.
Yes, and this tilt is also why the appearance of the rings changes so dramatically from Earth's perspective over its 29.5-year orbit. Sometimes we see them wide open, sometimes edge on.
And we already touched on the fact that different parts of the atmosphere rotate at different speeds, making that internal rotation so hard to pin down.
Right. Astronomers use different systems, like System I for the equator and System II for higher latitudes, to track the visible cloud movements. But finding that single solid body rotation period for the deep interior has been the real challenge, where ring seismology is now providing maybe the best answer.
Are there any other sort of oddities about its orbit or place in the solar system?
One interesting point highlighted in the sources is the apparent lack of known Trojan asteroids associated with Saturn.
Trojan asteroids. Those are the ones that share a planet's orbit, right? In stable spots ahead and behind.
Exactly. At the L4 and L5 Lagrange points, 60 degrees ahead and behind the planet. We've found Trojans for Mars, Jupiter, Uranus, and Neptune, but curiously, none have been confirmed for Saturn.
Why not? Is its orbit unstable for them?
The thinking is that complex gravitational interactions, especially the powerful influence of nearby Jupiter, create orbital resonances that destabilize those Lagrange points for Saturn. Essentially, Jupiter's gravity likely clears out any asteroids that might try to settle there long term.
So Jupiter, the giant neighbor, kind of bullies Saturn's orbital space, preventing it from having Trojan companions. Interesting.
It's a dynamic system out there.
And that dynamism definitely extends to Saturn's own family, its moons. It has a lot of them, doesn't it?
An incredible number. The sources list at least 274 known natural satellites orbiting Saturn. Now, only 63 of those have been formally named.
274. And that's not even counting.
Right. That doesn't include the hundreds of tiny moonlets, basically small chunks of ice and rock that are embedded within the rings themselves. It's a truly packed system.
And the undisputed king of that moon system has to be Titan.
Titan is just extraordinary. It's Saturn's largest moon by far, and it actually contains over 90% of all the mass orbiting Saturn. That includes all the other moons and the entire ring system combined.
90%. Wow. It really dominates.
It does. It's the second largest moon in the whole solar system. Only Ganymede at Jupiter is bigger. And Titan is actually larger in diameter than the planet Mercury, although it's less massive because it's mostly ice and rock.
But the truly unique thing about Titan is its atmosphere, isn't it?
That's the key differentiator. Titan is the only moon in our entire solar system known to possess a substantial, dense atmosphere. It's thicker than Earth's atmosphere, actually, mostly nitrogen, like ours, but with significant amounts of methane and ethane.
And this atmosphere allows for some amazing things.
It does. Complex organic chemistry is happening within that atmosphere, driven by sunlight and particles from Saturn's magnetosphere. It's like a prebiotic chemistry lab on a planetary scale.
Prebiotic chemistry, like the building blocks for life.
Potentially, yes. The sources mention the detection of compounds like polycyclic aromatic hydrocarbons high up, which are complex organic molecules. And perhaps even more strikingly, Titan is the only place besides Earth known to have stable bodies of liquid on its surface.
But not water, right?
Not water, no. The surface temperature is far too cold, around minus 179 Celsius. The liquids are hydrocarbons, mainly liquid methane and ethane.
So it has lakes and seas of liquid natural gas.
Exactly. The Cassini mission mapped extensive lakes and seas, particularly near the North Pole. The largest one, Kraken Mare, is almost the size of Earth's Caspian Sea. It even has rivers and rain cycles, but with methane instead of water.
That is just mind-blowing. A whole methane-based weather system.
It's incredible. There's even speculation mentioned in the sources that the nitrogen in Titan's atmosphere might not have come solely from the material that formed Saturn. Some think it might have originated much further out, perhaps from ammonia ice carried in comets from the Oort cloud.
So Titan's air might be partly from the edge of the solar system, Wild.
Mm.
Okay, but if Titan is fascinating for its chemistry, the moon that really gets people excited about life is Enceladus.
Enceladus, yes. It's become arguably the most compelling target in the search for extraterrestrial life within our solar system.
Why Enceladus specifically? It looks like a small, icy moon.
It is relatively small, only about 500 kilometers in diameter, but Cassini made a revolutionary discovery there. Geysers, plumes of water, ice, and vapor erupting from cracks near its south pole, the so-called tiger stripes.
Geysers shooting water into space.
Yes, over 100 individual geysers have been identified, and this was powerful evidence pointing towards a subsurface body of liquid water.
An ocean under the ice.
Exactly. Subsequent analysis of Cassini data, including gravity measurements and the composition of the plumes, strongly indicates a global or at least extensive regional ocean of liquid salt water beneath Enceladus's icy shell.
Liquid water, that's key for life as we know it.
It's essential. But Cassini found more. When it flew through those plumes in 2015, its instruments detected not just water and salts, but also simple organic molecules, silica nanoparticles, suggesting hydrothermal activity on the ocean floor, and crucially, molecular hydrogen.
Molecular hydrogen, why is that important?
Because molecular hydrogen can serve as a food source for certain types of microbes, specifically methanogens. These are organisms that on Earth live in environments without sunlight, like deep-sea hydrothermal vents, and combine hydrogen with carbon dioxide, which was also detected, to produce energy, releasing methane as waste.
So Enceladus seems to have liquid water, organic molecules, and a potential energy source.
Yeah.
Basically, the key ingredients for life.
Pretty much all the required ingredients for life as we know it, particularly for methanogenic life. This is what led NASA scientists back in 2011, even before the hydrogen discovery, to call Enceladus the most habitable spot beyond Earth in the solar system for life as we know it.
It's an incredibly tantalizing prospect. The sources also mention it's chemically similar to comets.
Wow. Just wow. Are there other interesting moons besides those two giant?
Oh, definitely.
Yeah.
Saturn has a whole menagerie. Some, like Rhea, the second largest after Titan, might even have a very tenuous atmosphere, or possibly even faint rings of its own, though that's still debated.
And some moons interact directly with the rings, right? Shepherd moons.
Yes. Small moons like Pandora and Prometheus orbit just outside and inside the F ring, and their gravity helps to confine the ring particles, acting like shepherds keeping the flock together.
That's a great image. Then you have moons like Pan and Atlas that orbit within gaps in the rings. Their gravity creates distinctive wave patterns like wakes in the nearby ring material.
And those waves are useful.
Very useful. By studying the characteristics of those density waves, scientists were able to calculate the mass density of the rings quite accurately.
Clever. And wasn't there even a hint of a new moon forming recently?
There was. In 2014, scientists analyzing Cassini images taken in 2013 spotted a disturbance, a bright clump, near the edge of the A-ring. It was nicknamed Peggy and interpreted as potentially being the very early stage of a new small moon coalescing out of ring particles.
So we might have actually witnessed the birth of a moon.
It's possible, or at least a temporary clumping event. It highlights that the rings are still a dynamic environment.
Okay, we absolutely cannot finish talking about Saturn's system without focusing properly on the star of the show, the rings themselves.
Absolutely. Saturn is probably best known, visually iconic, for its stunningly bright, extensive, and complex ring system. It's easily the most massive and conspicuous set of rings in the entire solar system.
Just how big are they? We know they're wide.
The main bright rings, typically labeled D, C, B, and A from closest to the planet outwards, plus the F, G, and E rings further outstretch from about 6,630 kilometers above Saturn's equator all the way out to 120,700 kilometers.
That's an enormous span. But they're famously thin, aren't they?
Incredibly, incredibly thin. On average, the main rings are only about 20 meters thick, maybe even thinner in some places, down to 10 meters.
20 meters thick, spanning over 100,000 kilometers wide. That scale is just hard to grasp, like a sheet of paper the size of a city.
It's an extreme aspect ratio. It's why they can seem to disappear when viewed edge-on from Earth.
What are they actually made of? Is it solid ice?
It's overwhelmingly water ice.
Yeah.
Billions upon billions of particles, mostly composed of water ice. That's why they're so bright and reflective.
Just ice.
Mostly, but not purely. There are also smaller amounts of rocky material mixed in, silicate dust, and some contamination by darker carbonaceous compounds, possibly complex organics called tholins, and maybe some amorphous carbon which can affect their color and brightness in places.
And the particles aren't all the same size.
Not at all. They range hugely in size, from microscopic dust specks, smaller than grains of sand, all the way up to chunks the size of houses, maybe 10 meters across or even larger in some cases.
And we know other gas giants have rings. Jupiter, Uranus, Neptune.
They do, yes. But Saturn's rings are in a class of their own. The others are much fainter, darker, less substantial, composed of dustier, less icy material. Saturn's really dwarf them in terms of mass and visibility.
Now, one of the really big debates mentioned in the sources is about how old the rings are. What are the competing ideas?
Right, this is a major ongoing puzzle. For a long time, the prevailing thought was that the rings were ancient, likely forming alongside Saturn itself, perhaps 4.5 billion years ago, maybe from leftover material or a moon that was shattered early on, perhaps during the late heavy bombardment period.
So, primordial, as old as the planet.
That was the traditional view. But data from the Cassini mission, particularly measurements of the ring's mass and the rate at which meteoritic dust is polluting the pristine ice, has led many scientists to argue for a much, much younger age.
Younger? How young are we talking?
Perhaps only about 100 million years old, maybe a bit older, maybe a bit younger, but certainly not billions of years old. In cosmic terms, that's very recent, like dinosaurs were roaming the Earth when Saturn's rings might have formed.
100 million years. That's practically yesterday, astronomically speaking. How would something so massive and spectacular form so recently?
The leading hypothesis for the young ring scenario is that they are the debris from a relatively large icy moon that got too close to Saturn.
It's straight inside the Roche limit.
Exactly. Inside the Roche limit, Saturn's tidal forces would have been stronger than the moon's own gravity holding it together, and it would have been ripped apart.
And the resulting debris spread out into the rings we see today.
That's the idea. One team supporting this theory even gave a name to this hypothetical doomed moon: Chrysalis. They proposed its destruction not only formed the rings, but might have also contributed to Saturn's axial tilt.
So ancient relics versus the recent dramatic shattering of a moon named Chrysalis, that's a pretty fundamental disagreement.
It is. Both sides have evidence supporting their models, and it's a very active area of research trying to reconcile the different lines of evidence. It's one of the big remaining mysteries of the Saturn system.
And beyond these main rings, there's another, much fainter one way out.
Yes, the Phoebe ring. It's incredibly sparse and vast, located far beyond the main system, extending out to maybe 12 million kilometers or more. It's associated with the irregular moon Phoebe.
And it's different from the main rings.
Very different. It's tilted by about 27 degrees relative to the main rings in Saturn's equator, and the particles orbit Saturn backwards in a retrograde direction, just like Phoebe itself. It's thought to be composed of dust kicked off Phoebe by impacts.
Fascinating. Okay, let's shift focus from the planet itself to how humans have seen it. We've been looking at Saturn for a very long time, haven't we?
Oh, absolutely. Saturn is one of the 5 classical planets easily visible to the naked eye, so observations date back to prehistoric times. And in early recorded history, it featured prominently in mythology and astronomy across many cultures.
The sources mentioned the Babylonian.
Yes, Babylonian astronomers systematically observed and recorded its movements. The ancient Greeks called it Phaenon, the shining one.
And the Romans gave it the name we use, Saturnus, linking it to their god of agriculture and time. And that's where Saturday comes from, right?
Yeah.
Saturni dies, Saturn's day.
Exactly. In Roman mythology, Saturnus was often equated with the Greek god Cronus, which is the name the planet still holds in modern Greek.
It had significance elsewhere, too.
Definitely. Hindu astrology knows it as Shani, considered a judge of people's deeds based on their past actions. Ancient Chinese and Japanese cultures associated it with the element Earth, calling it the Earth star in their 5-element system. And in Hebrew tradition, it's Shabbatai, linked sometimes with angels like Cassiel or spirits. It's amazing how this distant point of light was woven into so many different cultural frameworks.
But the real scientific understanding began with the telescope.
Right. Telescopic observation revolutionized everything starting in the 17th century. Galileo was the first to turn a telescope towards it back in 1610.
But he didn't quite figure out the rings, did he?
No, his early telescope wasn't powerful enough. He saw appendages on either side of the planet and famously sketched them, initially thinking they might be 2 large moons very close to Saturn. He was quite puzzled when they later seemed to disappear when the rings were edge-on.
So who figured it out?
That was Christian Huygens, a Dutch astronomer. Using a much-improved telescope in 1655, he correctly deduced that the appendages were actually a flat ring surrounding the planet not touching it. He published this in 1659.
And Huygens found Titan too, didn't he?
He did, also in 1655, a huge year for Saturn discoveries. Then, later in the 17th century, Giovanni Domenico Cassini made more key discoveries.
Cassini, the namesake of the mission and the gap in the rings.
Exactly. He discovered 4 more of Saturn's major moons, Iapetus, Rhea, Tethys, and Dione. And in 1675, he observed the major gap between the A and B rings, now known as the Cassini division.
Were other moons found later?
Yes, William Herschel discovered Mimas and Enceladus in 1789. The irregular moon Hyperion was found in 1848. And then Phoebe, the first known irregular retrograde moon, was discovered by William Pickering in 1899 from photographic plates.
And a key discovery about Titan came much later.
Yes, in 1944, Gerard Kuiper used spectroscopy to confirm that Titan possesses a substantial atmosphere, specifically identifying methane gas. This was a landmark finding, proving Titan was unique among moons.
But the truly revolutionary views came with the space age, with probes actually going there.
Absolutely. Spacecraft exploration completely changed our perspective. The first visitor was Pioneer 11, which flew by in September 1979.
What did Pioneer 11 find?
It gave us our first close-up images, though they were relatively low resolution. It discovered the thin, braided F-ring just outside the main O-ring, confirmed Saturn had a magnetic field, and gave us initial temperature measurements. It also noted the dark gaps in the rings appeared black, suggesting very little material in them.
Then came the Voyagers, which are maybe more famous for their Saturn encounters.
The Voyager probes provided the iconic images many of us grew up with. Voyager 1 flew by in November 1980, followed by Voyager 2 in August 1981.
And they sent back much better pictures.
Oh, vastly better. The first high-resolution images of the planet's atmosphere, the incredibly complex structure within the rings, and close-ups of many of the moons. Voyager 1 made a targeted flyby of Titan, but as suspected, its hazy atmosphere was opaque in visible light, so the surface remained hidden.
Did the Voyagers find new things too?
Yes, they discovered several small moons, confirmed the existence of the G-ring, observed intricate features like spokes in the B-ring, and provided much more detail on the atmospheric dynamics and the magnetosphere.
But the mission that really spent time there, that gave us the deepest understanding, was Cassini-Huygens.
Cassini-Huygens was, without doubt, transformational. It wasn't just a flyby, it was an orbiter. The Cassini spacecraft arrived at Saturn in July 2004 and spent over 13 years in orbit, studying the entire system in unprecedented detail, and it carried the Huygens probe.
Which landed on Titan.
Yes, the European Space Agency's Huygens probe successfully detached from Cassini and parachuted through Titan's atmosphere, landing on its surface in January 2005. It sent back incredible data and the first ever images from the surface of an outer solar system moon.
Cassini itself, its list of discoveries is just staggering, isn't it?
It's almost hard to summarize. It revealed dynamic clouds and weather patterns, including lightning storms thousands of times more powerful than Earth's. It provided definitive evidence for that liquid water ocean and the geysers on Enceladus, revolutionizing our view of its habitability.
It mapped the lakes and seas on Titan.
Mapped the hydrocarbon lakes and seas on Titan using radar, observed giant storms at both poles, including that hurricane-like vortex at the South Pole that might be billions of years old, and of course provided stunning views of the North Polar hexagon.
Did it find new rings or moons?
Yes, it discovered several new small moons, often orbiting within or near the rings. It also discovered previously unknown faint rings, like the one associated with Janus and Epimetheus. And as we mentioned, it captured those images hinting at the possible formation of a new moonlet, Peggy.
And it ended its mission in a pretty dramatic way.
It did. The mission concluded in September 2017 with the grand finale, a series of daring orbits where Cassini repeatedly dove through the unexplored gap between Saturn's innermost rings and the planet itself, gathering unique data before making a final, planned plunge into Saturn's atmosphere to avoid any risk of contaminating potentially habitable moons like Enceladus or Titan.
An incredible end to an incredible mission. Are there plans to go back? What's next for Saturn exploration?
Well, there are no currently funded missions on the scale of Cassini specifically for Saturn orbital science. However, the sources mention that Saturn's system, particularly its moons, remain high-priority targets. Several mission concepts have been proposed as part of NASA's competitive New Frontiers program.
Of what kind of missions?
Ideas include atmospheric probes designed to plunge into Saturn's atmosphere to measure its composition directly, which could help resolve questions about its formation and evolution. But the big focus is often on the moons.
Titan and Enceladus again.
Exactly. There's significant interest in missions specifically targeting Titan, like the proposed Dragonfly mission, A rotorcraft lander, basically a large drone designed to fly around Titan's surface, sampling different locations.
A flying robot on Titan. That sounds amazing.
It does. And for Enceladus, proposals often involve orbiters or even landers designed to sample the plumes more extensively or directly search for signs of life within that subsurface ocean. These moons hold such potential that they are prime candidates for future exploration.
Okay, shifting back to us here on Earth. How easy is it to see Saturn in the night sky?
Saturn is actually the most distant of the 5 planets that are easily visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. So yes, you absolutely can see it without a telescope.
What does it look like?
It appears as a fairly bright, non-twinkling point of light, typically with a steady yellowish hue. It's noticeably dimmer than Jupiter or Venus, but usually brighter than Mars, unless Mars is at its closest, and most stars.
And its brightness changes over time. You mentioned the rings tilt.
It does. Its apparent magnitude, or brightness, varies depending on 2 main factors: its distance from Earth, and significantly, the angle at which we're viewing the rings. It appears brightest when the rings are tilted most open towards us, reflecting the maximum amount of sunlight, and faintest when the rings are edge-on or nearly edge-on.
How long does it take Saturn to move through the constellations?
Because its orbit takes about 29.4 Earth years, it moves relatively slowly against the background stars, taking about 2.5 years to pass through each constellation of the zodiac.
And to actually see the rings, you need some help.
You definitely do. While Saturn itself is visible naked eye, resolving the rings as separate from the planet requires optical aid. Good binoculars might show it as slightly elongated, but you really need a small telescope, magnifying at least 30 times or so, to clearly see the rings as distinct structures.
And we talked about the rings sometimes disappearing.
Yes, that happens roughly every 15 Earth years, twice during Saturn's orbit. Earth passes through the plane of the rings, and because they are so incredibly thin, they seem to vanish for a short period when viewed exactly edge-on.
When's the next time that happens?
The next ring plane crossing is scheduled for 2025. However, unfortunately, Saturn will be very close to the Sun in our sky around that time, making it extremely difficult, if not impossible, to observe the disappearance effect then. We'll have to wait for the next opportunity.
When is the best time to observe Saturn generally?
The best time is usually around opposition. That's when Saturn is directly opposite the Sun in the sky from Earth's perspective.
So it rises around sunset and is visible all night.
Exactly. Opposition occurs roughly every 378 days, a bit more than a year, as Earth catches up to Saturn in its orbit. At opposition, Saturn is closest to Earth for that particular year and therefore appears largest and brightest, making it ideal for telescopic viewing. Its brightness at opposition still varies year to year depending on where Saturn is in its own elliptical orbit and that all-important ring tilt.
Can anything else block our view of Saturn? Like the moon?
Yes, occasionally the moon passes directly in front of Saturn, an event called an occultation. These don't happen every month because the moon's orbit is tilted slightly relative to the planet's paths. They tend to occur in series, maybe monthly for about a year, followed by a gap of several years before the geometry lines up again.
Interesting. And finally, the sources mentioned Saturn has also been a popular setting in fiction.
It has for a long time. Since at least the mid-18th century, writers have been setting stories on or around Saturn. Early depictions often imagined it incorrectly as a solid planet. Later, as our understanding grew, science fiction portrayed it more accurately as a gas giant, often focusing on its moons, especially Titan, as locations for adventure or mystery.
Makes sense. Titan and Enceladus offer such intriguing possibilities.
Definitely prime real estate for science fiction writers.
Wow. Okay, so from ancient myths, where it was a god, to modern science revealing things like diamond rain, helium rain, that bizarre hexagon, the complex organic chemistry happening on Titan, and maybe most excitingly, the very real possibility of a habitable ocean on Enceladus. This deep dive really shows a Saturn that's incredibly dynamic and mysterious, way more than just the planet with the pretty rings.
Absolutely. It really underscores how much complexity and, frankly, how much potential wonder is packed into these outer solar system worlds. Even places we've studied for centuries can still hold profound surprises, like the age of the rings or what's under the ice of a small moon.
It certainly reminds us that there's so much unexpected knowledge still waiting out there. So after digging through all this, what's the one thing that really sticks with you, that captures your imagination the most? Is it the hunt for life on Enceladus, the mystery of the ring's origin, that weird persistent hexagon?
It's hard to choose just one. Each aspect has its own fascination.
Definitely something for you, the listener, to think about too. What part of Saturn's story surprised you or sparked your curiosity? Plenty to mull over until our next deep dive.